Hi again, this is online class 11. Today we're going to cover section 6.5, the central limit theorem, Friday, October 26th, fall 2012. And this is math 125 at SUNY Cobblestone. I'm Carl Perez. Alright, I want you to pick it up with the central limit theorem. Very important topic. No kidding when we say it's central to the study of statistics, and we will be referring to this theorem for the rest of this course. Let me ask you to consider a scenario here. Consider. Let's say we've got a random variable x. Let's say it's normally distributed with some unspecified mean and standard deviation. Alright. I'm going to draw a little circle that represents all these x values, all the possibly millions of measurements, numerical values that make up this random variable x. Okay? If I plot the distribution of all these perhaps millions of x values, well, of course, we know what happens, right? Our horizontal axis represents all the possible x values, theoretically from negative infinity to positive infinity. Basically, you get a bell-shaped distribution. Why? Because that's what normal means, bell-shaped. The bell will peak at the population mean and will be spread out according to the standard deviation, whatever that value is. I want us not to lose sight of the fact that this envelope really indicates a piling up of numerical measurements below the envelope. So we see we've got most likely x values are in a neighborhood of the mean. Not too many high ones, not too many low ones. Most x values are somewhere in between, in a neighborhood of the mean, right? Alright, I want you to consider another situation. Scroll down. Consider this. We'll say we've got a random variable x, still with a normal distribution, still with some unspecified mean and standard deviation. I'm going to symbolize all those x values with a circle with dot 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 dot, meaning possibly millions of numerical measurements in this population, right? Well, what I'm going to do here, instead of plotting the distribution of all these individual x values, what I'm first going to do is I'm going to take a sample. I'll take a sample of size n. I'll compute the mean and record it. Then I'll throw the sample back. I'll take another sample. It may or may not overlap the original sample. I'll compute that sample mean. I'll take another and another and another sample of size n and compute all these different sample means. Now, if I keep doing this till the end of time, I'll have a list of millions, possibly, of sample mean values. And what I'll do here, instead of plotting the individual x values, I'm going to plot the distribution of all these x bar values, all the sample mean values. Alright, what's going to happen here is the sample mean process dampens or softens the effect of extreme values. Well, that means you'll be less likely to get a sample mean that's extremely high or to get a sample mean that's extremely low. If I was to plot the distribution, I'm wondering if I have enough room for it in this screen, of all these x bar values, let's see if I can get it down here. And again, the horizontal axis in this scenario will represent all my possible sample mean values. Well, the graph will still peak at the population mean, but it will be a narrower distribution. Let me get another color here. So, still bell shape, still normal, but a narrower bell. All right? The spread of these sample mean values will be less because of this dampening effect of extreme values. All right? All right, let me, doing the best I can freehand here, let me locate the peak of that sharper bell with another yellow line. All right, let me write down what I just said. The distribution of sample mean values will still be normal, in other words, bell-shaped, but with less spread. Or you could say that the bell will be narrower. Narrower bell, right? And as we know, standard deviation measures the spread, so if you've got less spread, that's equivalent to having a smaller standard deviation. Okay. And really that's what the central limit theorem is all about. Sample means have a normal distribution but with a smaller standard deviation. Let me write that down formally. Central limit theorem. If we are given a random variable x with a normal distribution and with some unspecified mean and some unspecified standard deviation, then I can say this, using the above discussion as a motivation. I could say samples of size n, and little n will refer to as a sample size as usual, have sample means that are normally distributed. Alright, set of sample means has a normal distribution. Alright, so what I could say is this. X bar is the variable that represents all the many sample means that we can have. We're claiming that X bar also has a normal distribution, but we can do better than that. When you say something is a normal distribution, you should ask yourself two questions. Of course, what's the mean and what's the standard deviation? And let me write that down here. I'll write this down in words first. The mean of the X bar values. In other words, the mean of the sample means. We denote that as mu sub X bar. And as we saw in our motivational discussion up above, the mean of the sample means will equal the population mean, the original population mean you're given. In other words, these distributions will peak at the same place. Now, the standard deviation of X bar values, again, we denote that with still with a sigma, but a sigma sub X bar, equals your original standard deviation divided by the square root of the sample size. Alright, and of course, when n is bigger than 1, when you divide by something that's bigger than 1, you're going to have something less than what you started with. So you can see the standard deviation here is going to go down when you're talking about sample mean distributions. Alright, so this, in essence, is the central limit theorem. Alright? Sample means are normally distributed with the mean that equals the population mean that you started with, but the standard deviation goes down by a factor of 1 over the square root of n. Alright, we can, again, hang on a minute, kind of show that graphically. If x is, hang on a minute, if a random variable x has a normal distribution with some unspecified mean and standard deviation, I can show that in a rough freehand graph. The bell here is peaking at the mean, and I claim I can graph the sample means of size n. X bar is also normal, still bell-shaped. The mean of all these sample means equals the population mean, but the standard deviation is going to decrease by a factor of 1 over the square root of n. And I can indicate this in this fashion. Again, I'll try not to exaggerate too much. Oops. I think we get the idea. Sample means will have a tighter, but still normal, bell-shaped distribution peaked at exactly the same place as your original population. Okay? Alright. How do we apply this central limit theorem to a problem type scenario? Let's look at exercise 5. Let me go back to yellow here. I think yellow turns out better. Let's look at exercise 5 on page 296. It's in your book, and one of your homework problems on the list. So please pause now and familiarize yourself with this problem and come back when you're ready to grind it out. Alright, we're talking about SAT scores here, right? We know, the book tells us, that the set of all SAT scores of all time, I'm going to denote that with a variable x. I'm going to let x represent all those millions and millions of SAT scores in all of history. The book claims that this variable of SAT scores has a normal distribution with a mean of 1518 and a standard deviation of 325, right? Alright, basically we've got two parts to this question. Let me kind of try to do them in parallel here, one next to the other. In part A, we randomly select one score. And we ask, what is the probability that a randomly selected SAT score is less than 1500? Well, you may say nothing new there. Didn't we talk about this in section 6.3? This is really a probability question in a non-standard normal situation. And of course, you're right. If I draw a quick little diagram here, the book always encourages us to draw a diagram so we don't lose sight of what's happening here. All these SAT scores have a normal distribution. They peak at the mean of 1518. which you recall the author gives us. I want the probability that x is less than 1500. Well, that's going to be a little bit left of the mean here. I'll indicate that 1500 location right here. So really what I want is the area onto the non-standard normal curve left of 1500, right? This area equals this probability. Of course, I can find that with my normal CDF command. And we did this before in section 6.3. Theoretically, these x values go off to negative infinity, and our author says to use minus 999,999 to approximate negative infinity. Our upper bound is going to be 1500. Our mean is 1518, and our standard deviation is 325. Alright, so I can easily calculate this area, this probability, using the full power of our calculator, and I'll call that 0.4799. Oops, let me fix that. Erase the whole thing. 0.4779. Put a nice box around it. Alright, and that's the answer to part A. Alright, nothing new there. Alright, that's 6.3. What about 6.5? Well, part B talks about section 6.5. If we randomly select not just 1, but 100, we want the probability that the sample mean is less than 1500. Well, I can symbolize that like this. And notice the very subtle, seemingly subtle, but really very profound notational difference. In this problem, we're talking about a single x value. In this problem, we're talking about the probability of a sample mean from a sample size of 100. Alright, let me erase this piece, because I'm going to need some more room here. I'm having trouble today. Alright. Alright. Well, we know that all possible sample means of size 100 has a normal distribution. The central limit theorem tells us that. The mean of all these sample means is equal to the population mean, which is already given to us as 1518, right? The standard deviation of the sample means is going to be your original SD divided by the square root of the sample size. Now the original SD, you recall, was 325, and the sample size was 100. So I want to divide this by the square root of 100. Alright, so of course I can easily do this in my head. Square root of 100 is 10. If I take 325 divided by 10, I get 32.5. Alright, so let me rehash that. The set of all sample means is normally distributed. The mean of the sample means equals 1518, and the standard deviation of the sample means is going to be 32.5. Alright, once I know things are normal and I know that the mean and standard deviation is, I can easily grind out probabilities between any limits I like. Alright, so the probability that x bar is less than 1500 here. Well, again, let me draw a little bit of a picture. I'll draw a sharper distribution here, a narrower distribution of x bar values, indicating we're talking about sample means here. The mean is still going to be 1518. 1500 is somewhere here, and this is the area I seek here. Now, of course, I'm going to use my normal CDF command to find it, but something's changed. Normal CDF. We're going to go off to negative infinity. In theory, my upper bound is going to be 1500. My mean is going to be the same at 1518, but what changes is the standard deviation. 32.5 instead of 325 as we had before. If we grind this out, I get 0.2898. And that's my final answer for part B. Okay? Alright. You can see it differs from part A. Part A is up screen here. Part A, the probability that one random value is less than 1500, it's about a half. And the probability that a sample mean is less than that value, certainly less than a half, right? Alright, so that's example, actually homework exercise 5 on page 296. Let me do another homework exercise for you. I get a new screen here. Let's consider exercise 8. On page 296, also in your homework list. Still talking about SAT scores. So we know that SAT scores, represented by variable x, are normally distributed with a mean of 1518 and a standard deviation of 325 as before. This is in the same set of problems as the first example we did, right? Alright, again, let's break this up into two types of problems. I want to work this out in parallel. Again, in part A, we randomly select 1. In part B, we're going to randomly select 16 SAT scores. Alright, here in this problem, in this part A, for number 8, they want the probability that a randomly selected SAT score is between 1440 and 1480. And in part B, they want the probability that a randomly selected, when we randomly select 16, I should say, the probability that a sample mean from these 16 is between the same limits. So notice the slight notational difference, but the problems are very different. Alright, again, let me draw a little picture here. X is normal. The SAT scores have a normal distribution that peak at the population mean of 1518. And if I draw lower and upper boundaries here, 1440 and 1480, this area under the normal curve is the probability we seek. So I'll use my normal CDF command on calculator. Again, you plug in a lower bound, an upper bound. We're in a non-standard case, so you've got to plug in a mean and a standard deviation, 325. And if I punch that out, I get 0.0483. And again, nothing new there. That was really a section 6.3 type problem. How about part B? Well, let me get another color here again to indicate we're talking about sample means here. Sample means still have a normal distribution. they still peak at the population mean of 1518. What happens as the standard deviation changes? You see up a narrower bell. I hope I'm not exaggerating this too much. Right, we're still interested in the same limits of interest. We got a narrower distribution to deal with here. Alright, so this probability that I seek is that area, that's a 1440 there, is that area under the non-standard normal curve between 1440 and 1480. Of course, I'll grind this out with my normal CDF command. Alright, the lower limit will be 1440. The upper limit will be 1480. The mean is still 1518. But what happens is the standard deviation changes, right? Instead of 325, you want to plug in 325 divided by the square root of the sample size, which is 16. Now you can work this out ahead of time and then plug it into your normal CDF command, or you can type it into your calculator. You would need a 325 / root 16 and then close the square root. Any way you like to do it is fine, as long as I get the correct answer. I'll call it 0.1515. Alright, so certainly since the shape of the curve changes, the probabilities will also change. Okay? Alright, one more example I want to talk about before we call it a day today is example 2 on page 290. Now, this is not a homework exercise. This is an example given in the book. So, example 2 on page 290. So please familiarize yourself with that example, read through it, and come back when you're ready. Please pause now. Alright, here we're going to be talking about men's weights. Alright, similar scenario as in the previous two examples. You're going to be talking about a sample, one randomly selected value in part A, and then you're going to talk about a mean from a sample of size 20 here in part B. Alright, let me summarize what the book tells us first. We're talking about adult men's weights. I'm going to let the variable x represent all men's weights of all time. And the author claims that these weights are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Alright, that sounds reasonable. And again, let me break it up into part A. I wish I knew why this screen was flitting around. Alright. Part A and part B as before. Again, in part A, we'll randomly select one. And in part B, we're randomly selecting 20. In part A, we want the probability that a single randomly selected x value is greater than 175, or a randomly selected man has a weight greater than 175. And again, in part B, from this sample of size 20, we're going to compute a sample mean. And I want the probability that the sample mean weight is greater than 175. And again, a slight notational difference. But again, a very profound problematic difference. In part A, if I take a moment to draw a little picture, Men's weights are normally distributed with a mean of 172. Alright, 175 is certainly right of the mean of 172. And in this non-standard situation, I'll want the probability that a randomly selected weight is greater than 175. In other words, the area under this non-standard normal curve to the right of 175. As usual, we'll punch this out with my normal CDF command. Alright, now if I'm looking for this area, remember, theoretically, these x values go off to positive infinity. So I'm going to plug in a left boundary of 175 and a right boundary of 999,999, as our author has told us, a mean value of 172, and a standard deviation of 29. I punch this out in my calculator, and I get 0.4598. And that's the probability I seek in Part A. Okay? Let's talk about Part B now. Alright, remember we randomly selected 20. What's the probability that the sample mean from that 20 is greater than the same limit as given in Part A? Well, we know sample means have a normal distribution. The mean of the sample mean equals the population mean, which we were told is 172 in this problem, right? The standard deviation of the sample means, of all possible sample means, is your original SD divided by the square root of the sample size. And here that's going to be 29 divided by the square root of the sample size is 20. Alright, so again I can make another little curve here. Help me visualize this problem. X bar values will be normally distributed, still bell-shaped. Still the peak will occur at 172. But because the standard deviation is being divided by something bigger than 1, you're going to have a sharper, narrower, bell-shaped distribution. Again, I hope I'm not exaggerating too much. Alright, we're still interested in the same limit as Part A. So I'll draw a boundary of 175 somewhere to the right of the mean. This area is the probability I seek. So again, I can grind this out with my normal CDF function. The left bound is going to be 175. The right bound, remember, these x values theoretically go off to forever. So I'll plug in 999,999, our best approximation for infinity. In the non-standard case here, our mean is 172. And our standard deviation, well, remember that changed. It's 29 over the square root of 20. And again, you can grind this out ahead of time and put in a decimal approximation. I like to plug it into the calculator just like I see it there. Let me show you how to do that. Need a little more room here. I'll do 29 slash root 20 and then close your root. Alright. Of course, you got to close your parentheses of your normal CDF command. And I'll let the calculator do as much work as I possibly can. If I punch that out, I get 0.3218, and that's the probability I seek. Alright, I think we've covered all possible scenarios in this. So we had the probability that a sample mean is less than a value, probability that the sample mean is greater than a value, and the probability that a sample mean is between two values. So we covered all bases here, and the types of things you'll see in your homework list. So we'll call it a day. It's about the 35-minute mark. So this concludes Online Class 11 in Math 125 Fall 2012. That is all.